I think we live at a really crucial time in the history of ideas. It's a time where, for the first time, we have what begins to be a global view of the universe that we live in. We have a cosmological model that tells us that the universe was much hotter and denser in the past. The Big Bang framework of thinking about the history of the universe. We can cast our minds back to the epoch when the universe was completely dark. No starlight had yet been produced. And so there is a time when the stars light up. So just the fact that we can say these things, and then not just stories, but they really are based on hard scientific evidence. I think that combination is really what excites me about being a cosmologist. As I said, we've reached really an unprecedented level of understanding of our physical universe, but there are still some very troubling open questions, mysteries, enigmas that we just really do not have an answer to. For example, we know that the universe is accelerating its expansion. This is sometimes called by the name dark energy. There's some dark energy that appears to be causing the universe to accelerate. And we really do not understand what this dark energy is. We can put terms into the equations that model this very precisely, and it's not mathematically very complicated, but really everything we know about fundamental physics tells us that these terms should be much larger generically. Or maybe you can arrange things in such a way that they're completely zero, but having this tiny little value that is very clearly distinct from zero that we observe in the universe, that's something incredibly surprising. And so how do we go out and how do we learn about this? And so upcoming surveys, galaxy surveys, actually map out this expansion history, how the universe accelerated in detail over the last billion years or so. And one of my research interests that I'm developing now is to look in the areas of the universe that are empty or almost empty, because those are the places that are dominated by dark energy. And if we look at how these areas change over time, what their characteristics are, how they interact with the matter that's around them, to try to really probe dark energy as a physical thing, see how it behaves when it gets perturbed, what happens, how it pushes those regions apart. And then even the slightly less mysterious, but nevertheless still unsolved problem of dark matter. We do have some dark matter candidates. There are some ideas about what the dark matter could be from a fundamental physics point of view, extensions of the standard model of particle physics. But so far, we have not actually directly detected dark matter particles, nor have we actually produced them directly in particle accelerators. And so this remains a mystery, because wherever we look in the universe, we find that there appear to be clumps of matter that attract other visible matter around them. Just very recently, with the first release of the Planck results, it turns out that we see evidence for this dark matter even in the cosmic microwave background maps, these maps of microwaves coming from the sky. These microwaves traveled through the entire universe. And in Einstein's theory of relativity, clumps of gravitating matter, like dark matter, deflect light that travels around them. And we see evidence for this deflection in these microwave maps from the cosmic microwave background. And so we have really a map of the integrated matter density of the entire universe all the way back to when the afterglow of the Big Bang was emitted. So this is something really new that just happened, and based on this, new surveys are being planned. There are new observational campaigns, large observational campaigns. They're usually very international in nature, with lots of collaborators from different countries, to map out the density of galaxies in the entire universe, and then to use very distant galaxies as sources and understand how their light gets deflected by the dark matter distribution between us and them. And by doing that at different distances, you can actually build up a three-dimensional map of the dark matter, make dark matter visible through its gravitational effects, which is a really exciting prospect. So in 3D, now we've done it with Planck in 2D, but this can do it in 3D. And that will really give us a much better understanding of the properties of this still mysterious component of the universe.